Hey everyone, welcome back to the College Algebra playlist. In this video, we're going to take a look at some examples where we use exponent rules and we also use radical and rational exponent rules to simplify messy algebraic expressions. Okay, before we dive into the examples, I just want to give you a quick review of everything we looked at in the previous two videos. All right, these are the exponent rules that we took a close look at. Okay, so I want to encourage you to pause the video and just take a moment to write these down in your notes if you haven't already done so. These are the rules we're going to use to simplify algebraic expressions. Okay, and we're also going to use the radical and rational exponent rules listed here. Okay, radicals and rational exponents are interchangeable, as we can see here. And we need to use these rules to switch back and forth between the two. Okay, so this business in blue here, what I have written down, don't worry about this too much. These are just some conditions that we need to specify when this equation is true. Don't worry about those too much. Instead, just focus on the rules themselves. Okay, when we break radicals up into two pieces like this, this is what it looks like. I'm just including these conditions here as a formality. All right, so jot these down in your notes as well. And let's dive in. Here we go, example 13. I'm asked to simplify the expression 3 squared times 3 cubed. Okay, here I have the same base being raised to 2 powers, and they're connected by multiplication. So the rule says to take those exponents and add them. So I have 3 to the 2 plus 3. 2 plus 3 is 5, so I have 3 to the 5, which is 243. And you can plug that into your calculator and double check that that's right. Our final solution is 243. Here I have 2 squared whole thing to the negative 3 power. What I want to do here is multiply the exponents. Okay, this is a power on top of a power rule. All right, this is where we multiply the exponents. Okay, so I have 2 to the 2 times negative 3. 2 times negative 3 is negative 6. Oftentimes when we simplify expressions like this, we're asked to report the final answer using only positive exponents. So instead of 2 to the negative 6, I want to turn that exponent positive by bringing it to the denominator of a new fraction. Okay, so 2 to the negative 6 is equal to 1 over 2 to the positive 6. Okay, and 2 to the 6 is equal to 64. So that's what I have in the denominator. My final answer is 1 over 64. Here I have 11 to the 4 divided by 11 to the 5. I'm going to rewrite this as a fraction. Okay, this is the way we're used to seeing it. This is what the exponent rule looks like. Okay, so I have 11 to the 4 over 11 to the 5. In this example, right, the rule I want to use says to subtract the exponents. Okay, so I have 11 to the 4 minus 5. All right, that's going to give me 11 to the negative 1. Once again, I want to report my answer with positive exponents. So let's take that to the denominator and turn the exponent positive. I have 1 over 11 to the 1, and anything to the 1 power is just equal to itself. So on the bottom, I just have 11. All right, so this is 1 over 11. This is my final answer. All right, moving on. Here I'm asked to simplify, and I want to write my final answer with positive exponents. Okay, no problem. We should be able to do that if we know how to use the exponent rules effectively. Okay. Here I have x to the 4th times x to the 3rd over x squared. In the numerator, I can use an exponent rule to condense this down to one base, and I can add the powers, 4 plus 3. Okay, that's what the rule says to do. Okay, so up top I just have x to the 7. All right, now I want to use another exponent rule to simplify this further. X to the 7 over x to the 2 is equal to x to the 7 minus 2. Okay, And 7 minus 2 is just 5. So I have x to the 5, and that's my final answer. Okay, here I have a cubed times b to the 4th, whole thing being squared. Okay, so look at what I have in the parentheses here. I have something times something. Okay, I have a cubed times b to the 4th. All right, there's an exponent rule that says I can take this power and apply it to each piece of the product. Okay, so I'm going to take this 2 and apply it to a cubed, and I'm going to also apply it to b to the 4th. Okay, so I have a power on top of a power. What do? I multiply the exponents in both cases. All right, so I have a to the 3 times 2 times b to the 4 times 2. All right, that gives me a to the 6 times b to the 8. So my final answer is a to the 6 times b to the 8. Here I have something slightly more complicated. Okay, so let's handle this. Let's handle this carefully by looking at one exponent rule at a time. Okay, I have in blue here x to the negative 3 over x to the positive 4. So the rule says to subtract the exponents. Okay, I have the same base to 2 powers and they're connected by a quotient. That's when I subtract the exponents. All right, so I have x to the negative 3 minus 4. That equals x to the negative 7. Okay, so we've taken care of the x's. Next, let's take care of the y's. All right, I have y to the 2 over y to the negative 3. I want to use that same exponent rule to collapse this down to just one y. Okay, just one base y. All right, so this is what I have. In blue, I have x to the negative 7, and in red, I have y to the 2 minus 3. Now, I've just made a mistake, and I'd like you to take a moment to see if you can spot it. Okay, where did I make the mistake? The rule says to subtract the powers, okay, and not add them. Okay, so what I actually need here is y to the 2 minus negative 3. Okay, that looks a little goofy, but that's okay, we can handle that. Minus a negative, that's just an addition. Okay, so I'm just doing 2 plus 3 here in red. That gives me y to the positive 5. Okay, so I almost have my final answer. I just want to clean it up a little bit and write my final answer with only positive exponents. Okay, so let's take this x to the negative 7 and bring it to the denominator of a new fraction. Okay, and that's how we can turn that exponent positive. So my final answer is y to the 5 over x to the 7. Here I have x to the negative 2 times y to the 12 divided by y to the 0, and that whole thing is being raised to the 2 power. The first thing I notice is that I have y to the 0 here. Okay, anything to the 0 power is just equal to 1. All right, so that's an exponent rule that we have. All right, x to the negative 2 times y to the 12 divided by 1, we really don't need that divided by 1. Okay, anything divided by 1 is just equal to itself. Okay, so we have x to the negative 2 times y to the 12, and the whole thing is being raised to the 2 power. All right, once again, I want to apply that exponent to each piece of the product. Okay, so this is what I have here. And when I have a power on top of a power, what do? I multiply the exponents. Okay, that's what we want to do here. So this gives us x to the negative 4 times y to the 24. All right. Once again, I need to report my final answer with only positive exponents. So let's take care of that by bringing x to the 4 to the denominator. So my final answer is y to the 24 over x to the 4. Okay, next we're going to venture into the realm of radicals and rational exponents. Okay, so we're going to use those 3 rules we learned to clean up these messy expressions. Okay? The square root of 4 times 9 plus 16. All right, the first thing I want to do is deal with this business in parentheses. Okay, 9 plus 16 is 25. Okay, so I have the square root of a product, right? I have the square root of 4 times 25. And there's a rule that says that I can break that up into 2 different radicals. So that's exactly what I'm going to do. okay? And 4 and 25 are actually both perfect squares, so these clean up really nicely. This gives us 2 times 5. Okay, the square root of 4 is 2, and the square root of 25 is 5. So 2 times 5 equals 10. So our final answer is 10. Okay, here I have the square root of 27 over 64. So what I want to do is break this up into 2 separate radicals. Okay? On the bottom I have a perfect square, so that's going to clean up nicely. But in the top, it's a little bit trickier. I actually want to find a perfect square that's hiding in there. Okay, I want to say that 27 is the same thing as 9 times 3. Now why am I doing this? Because I want to break this radical up into 2 pieces, right? So when I do that, I have the square root of 9 times the square root of 3, and 9 is a perfect square. So that's going to clean up nicely to just give us 3. Okay, what I have in red here is 3. So my final answer is 3 root 3 over 8. Next, I have the square root of 400 times x to the 4th. Okay, so in these next examples, we're going to introduce some variables in the radical expressions. Okay, so it's going to get a little harder now. Okay, so we have the square root of 400 times x to the 4th. I'm going to break that up into 2 pieces, right? This is a product that's under the radical, so I can break this up into 2 different radicals. The square root of 400 is just 20. Okay, so that cleans up nicely. And the square root of x to the 4, I'm going to rewrite that as a rational exponent. Remember, radicals and rational exponents are interchangeable. So I don't have any index here, so when the index is blank, it's assumed to be 2, right? The index of this radical is 2. So I take that 2 and I bring it to the denominator of my rational exponent, and I take the 4 and I bring it to the numerator of the rational exponent. Okay, so the square root of x to the 4th is equal to x to the 4 over 2. Okay, 4 divided by 2 is just 2. So we're left with 20 times x squared. That's my final answer. Last example. This is a super hard problem, okay? So buckle your seatbelts. This is going to take us a while to simplify. Okay, but let's just take it one step at a time. All right, I have the cube root of a quotient here. Okay, this is a pretty messy expression, so we want to do everything we can to clean it up. All right, I'm going to break this up into 2 different radicals, okay? It's the cube root of something over the cube root of something. All right. Next, in the numerator and in the denominator, I'm going to break this up again into 2 pieces, right? The cube root of 81 times x to the 5th, that equals the cube root of 81 times the cube root of x to the 5th, up top. And on the bottom, the cube root of 8 times x cubed is the cube root of 8 times the cube root of x cubed. Okay? So let's handle the variables first. Let's take care of the variable business first. Okay? The cube root of x to the 5 is the same thing as x to the 5 over 3 power. Okay? So this is what we have. And then in the denominator, we have x to the 3, and we're taking the cube root. So I can rewrite that as x to the 3 over 3. That's what the radical exponent rule says to do. That's what the rational exponent says to do. I'm sorry. Okay, so what we have is x to the something over x to the something. All right, so this business in green, what I can do is I can condense the base into 1 and subtract the powers. Okay, and we already have a common denominator, so this fraction subtraction is fairly easy. We're just left with x to the 2/3 power. Okay, because 5/3 minus 3/3 is 2/3. Okay, so now here in front of the x, I have this ugly radical business. Okay, so let's clean that up. Let's take this whole expression and bring it to the top of the screen. Okay, this is what I have. So the cube root of 81, I'm going to rewrite that as the cube root of 27 times 3. Okay, I found a perfect cube that's hiding in here. Okay, so when I do that, I can break it up into 2 radicals, right? And the reason I want to do that is because the cube root of 27 is just 3. This is what I have in blue here. Okay? So next, what I want to do is notice that in the denominator, the cube root of 8, that's another perfect cube. That collapses down to just 2. So in green, I have 2. All right, this number right here, this is our final solution in terms of simplifying the constants, right? It looks a little ugly, but this is just a number. Okay, this number in red here, it's approximately equal to 2.16. Okay, but I don't want an approximate answer here. I'm going to report the exact answer with this radical. Okay, so my final answer is 3 times the cube root of 3 over 2 times x to the 2/3 power. So what I had in the beginning, I'm putting that on the left here. This whole thing ended up equaling this business on the right. So that does it for this video. Thank you for watching, and like and subscribe.